Okay, so this first one, we are going to write this sigma notation as an integral. So when you, I like that you guys chose like to go out of the box a little bit, do a couple different ones. That's good. Yeah, we haven't, my first period still has not picked up on the shifting possibility, but it really doesn't matter. You're fine either way. As long as it meets all the requirements, it's okay. So here's the thing. So we know our width is 9 over n. So our b minus a over n is 9 over n, which means that b minus a, or the difference between the left and right endpoints, has to be 9. All right, so we all got that. So now, what are we plugging into our function? Remember that typically what we plug into the function is left endpoint plus width times I. So if you look and you see left endpoint plus width times I, then this number, that could be your left endpoint. And you ask yourself, what am I plugging left endpoint plus width times I into? Whatever you are, just replace that with the letter x, and that's your function. So our left endpoint is -4. To get from left to right, we have to go a distance of 9, so our right endpoint would be 5. And then what are we plugging left endpoint plus width times I into? We're plugging it into x cubed. And don't forget the dx. So as a couple of groups, good morning, pointed out pictures. As a couple of groups pointed out, this is the same as if we did the integral from 0 to 9 of -4 plus x cubed dx. Because if you start at 0, then you're plugged, like this is just hard-coded into your function, and so your left endpoint plus width times I would just be the 9i over n. What are you plugging it into? -4 plus x quantity cubed. And you end up with the exact same integral. It's the same space, because this function is just this. Oh my gosh, this is going to make me sick. There we go. Stop shaking. This function is just this function shifted 4 places to the right. So if you shift your limits 4 places to the right to adjust, you end up with the exact same area. Whew. Okay, use geometry to evaluate. So whenever I have to do an integral with geometry, you're going to want to sketch the graph, right? All right, so we have 3x plus 4 evaluated from -1 to 3. So what kind of a shape is this? Well, it would be helpful to know where -1 falls on this graph. So if you don't know, just plug the -1 in. -3 plus 4 is 1. So let's just say that's the point, -1, 1. That's a negative. Okay. And then at 3, you plug in a 3 and you get 13. So all right, so the value of the integral, this one we actually took it easy on you because it's all above the x-axis. They won't all be today though. It's the area of this shape. So first question of the day, what kind of a shape is this?
Trapezoid.
It's a trapezoid. Very good. If you do not know the area of a trapezoid, which you will have to know when we do area by trapezoids, but if you don't know it right now, you could break this into a rectangle and a triangle. All trapezoids can be broken into rectangles and triangles, right? So you could break it into a rectangle and a triangle and add them together. If it doesn't scream to you trapezoid, because I know in geometry we're taught trapezoids all look like that, right? This is actually, it's turned sideways, right? Think of it as this shape, right? Turned sideways. So that's the shape that we're looking at, right? So area, so our integral would, so our area would be, it just equals, not approximately, it equals. Okay, so area of a trapezoid is 1/2 sum of the bases times the height of the trapezoid. Since it's turned sideways, the height is actually this way. So you end up with 1, 2, 3, 4 as your height. And then you have this base has a height of 1. and this base has a height of 13. So we end up with 2 times 14, or 28, which, yes. Whoa! Okay, so you guys got to read the directions, right? Oh, we don't know geometry, only calculus? Okay, except that you got it wrong, so. All right, so. Yeah, so the second one was great. First one you guys evaluated. Okay, you got to read the directions. All right, you guys rocked, so well done.
Yeah.
Yeah, no, that's great. It's either numerically equivalent to correct is correct. You guys did it perfect, right? Good. Okay, so this one, let's see, is it negative 4 plus x? Yeah, that's right. Good. I'm going to erase this so that you guys don't sneak and see an answer to the later problem. Okay. Good. Fantastic. All right, well done. I'm going to pause for a second and tell you a 2-second math controversy. All right, today we're doing the first day of the fundamental theorem of calculus. We're doing FTC part 1. FTC, not Federal Trade Commission, fundamental theorem of calculus. Again, this is something that kind of freaked me out a little bit this year because for the last 20 years, well, I guess that's not true. I've only been teaching calculus for 17 years. So for the last 17 years, I have taught what we're doing today as FTC Part 2 and Monday as FTC Part 1. But your book says this is FTC Part 1 and Monday's is FTC Part 2. And the source of all knowledge, Wikipedia, agrees with your book, so we're going with it, right? So, yeah. Okay. Let me pause record. The fundamental theorem of calculus is the topic that bridges the 2 branches of calculus together. So I don't know if you know, calculus has 2 branches. There's differential calculus and there's integral calculus. Differential calculus is all the derivative stuff. Integral calculus is all the integral stuff. The fundamental theorem of calculus is a theorem that puts those 2 things together. So in the fundamental theorem of calculus, you have derivatives of integrals and how on earth do they interact. So, okay. So it gives the precise inverse relationship between the derivative and the integral. So what we're going to do is, we all know, deep down, if I start the function and I take the antiderivative and then I differentiate it, I should end up back at the function, right? Same thing vice versa. If I differentiate it and then I anti-differentiate it, I should end up back at the function, right? Okay. So what the fundamental theorem of calculus does is it kind of proves that in this kind of unusual way that we are now calling part 1. So here we go. So in order to understand the fundamental theorem of calculus, you first have to understand a new type of function. So f of t is this function right here. It's this basically this boundary, right? So f of t is some regular old function that we have graphed right here. We are defining a new function called g of x, where g of x is the integral from some constant a to some input variable x under f of t dt. So g of x is now like an area finding function. So it's a function where you input an x value and what you get out is the area from a to x under the graph of f. Okay? So this g function now, it's an integral function. So what is it really? It's like an area finding function under the graph of f between a and some input value. Now, first question that you have to learn how to get comfortable with is the fact that we have two variables on the same axis. So this axis right here, when we input values into F, we're inputting T values. When we input values into G, we're inputting X values. Yet, they represent same numbers on the same number line, right? Now, why do we need different letters? Because if we call this F of X, and I said, what's G of 5? You'd be plugging a 5 both in here and in here, and you'd end up with an integral of a constant, which would just be 0, and which would just be a rectangle. It would change the function to a constant. So you don't want it, when I plug a number in, I only want it to go here. I don't want it to go both places. So because of that, I have to use different letters here and here. It's simply so that if I want to plug a number into F, like I say, let's let T equal 7, right? If I want to plug a number into G, let's let X equal 3, and it's only going into G. Okay, so you have to have two different variables whenever you have these funky integral functions. Okay, so in essence, the real thing, like on this screen, all you need to know is that G finds area. So the next screen, all we're going to do is practice this before we learn the actual FTC. Okay, so I have this beautiful function f of t, and G is defined as the integral from 0 to x of f of t dt. So if you have to find G of 0, 1, 2, 3, 4, and 5, so let's just find, I'm going to find G of 0 with you together. So G of 0 means you're taking a 0 and you're plugging it in there for your upper limit of your integral. So G of 0 is the integral from 0 to 0 of f of t dt. And as you learned yesterday, what's the integral from 0 to 0? 0. Okay. All right. So just on paper, there's going to be a lot of whiteboard stuff today, but not this. So on paper, I want you to figure out G of 1, G of 2, G of 3, G of 4, G of 5. Just a little warning, G of 3 and G of 5, those will just be estimates. I don't want you, I'm not going to give you an actual function. So when you're figuring out this area, you can just kind of guesstimate it. That's fine. All right, so take a minute, see if you can figure out all of these. Oh, I gotta pause this. So this is the integral from 0 to 1. So the integral from 0 to 1 is the area of this triangle, which is 1/2 times 1 times 2, or 1. So everyone good with that? Yes. All right. G of 2 is the integral from 0 to 2. If you ever have to do these on the AP exam, you do have to write the integral. Like, always show that what you're plugging the number into. Usually the integral is worth a point. So the integral from 0 to 2, so we're taking this and we're adding this lovely rectangle. So G of 2 would be 3. All right. G of 3 is the integral from 0 to 3. So this estimate right here, we know it's a little bit more than 1. If you used 1-ish, I mean, that's okay. If you wanted to go like 1.5 or 1.3, any of those would be fine. What did you guys use? 1? 1.5? All right, we'll call it 1. All right, so then that means G of 3 would be around 4. All right, G of 4, I said, was exact. Now, we don't have proof that this area and this area are the same, but they look pretty much the same. So to me, it was like kind of a safe bet that they were the same. So anyway, if this is 1, this area is also around 1, except for this guy, for the integral, this area has to be negative. So you add it, you subtract it, you get a net of 0. So this integral just goes back to 3. All right. and then g of 5 okay, which is approximate. This is approximate too. All right, so g of 5, so now we've got this, which is also, we're going to just call it 1 again, except when we add it to our integral, we have to make it negative. So you get 3 plus 0 minus 1. So g of 5 is roughly 2-ish. How did we do on those? Did you guys remember to make this stuff below the x-axis negative?
Yeah.
Yes, good. Okay. All right, so if you're plugging numbers into an area finding function, that's what that means. You just plug it in for your limit and find the area. All right, now this is the how. You don't have to write this. This is explaining how the FTC is derived. So I'm going to walk you through it. This is not something you have to know. This is just explaining why does it work, right? How did we come up with it? So how did they? Okay, how did they come up with it, right? All right. So when we start with this, the first thing that we have to notice, and these pictures are kind of small. Here, wait. I'm gonna make there, just so you can see the pictures better. All right. Okay. So FTC Part 1 deals with finding the derivative of an integral. So we're going to kind of break it down. So we've already established f is your border function, g is your area finding function. So the first thing that we're going to do is we're going to say, if I had g of x, and that gave me this area, well, if I found g of x plus h, if this was x plus h, that would give me this area, right? So if I did g of x plus h minus g of x, it's this whole area minus this area, which leaves you with just this little guy right here. So g of x plus h minus g of x is roughly the area of that rectangle. Now, it's not exactly, because technically that's a rectangle, and truly g of x would be like that, right? The g of x plus h minus g of x would be like that. So anyway, so if we call it a rectangle, that's an approximation. But let's just think about this. So we have g of x plus h minus g of x. Well, that's roughly the area of this rectangle. Well, the area of this rectangle, the width, what's x plus h minus x? H. So the width would be h. And then the height, well, this is our function, right? F of x is our function, really, f of t. But anyway, so our height would be, f of t, right? So we're going to call it f of x now because we're not in integral mode. Later on, we have to switch the variable. But right now, we can go ahead and use x. All right. So the area found by taking g of x plus h minus g of x is roughly the same as h times the height of your function at the value x, right? It's not exact, but it's roughly the same. Okay. So, what if we took this h and put it down there? Well, then we have g of x plus h minus g of x over h equals f. So if we have g of x plus h minus g of x over h is approximately equal to f, well, what if we took the limit as h approaches 0? If we take the limit as h approaches 0, then this would be equal, right? Because this and this, well, this would be just a line essentially, and what would be that line? It'd be the height of your function. All right? Oh, but what does the limit as h approaches 0, g of x plus h minus g of x over h equal? That's g prime by definition, right? So what we've just said now is if g equals this, and actually this could be any value, but it doesn't have to be 0, it could be any a. If g equals this, then g prime equals f of x. And that's the fundamental theorem of calculus. It's kind of weird. This is it right here in like nice print. So it's kind of weird, but this is the beginning of the fundamental theorem of calculus. So because we're going to expand it to a more general case in a minute. So FTC part 1, if f is continuous from a to b, then the derivative of the integral from a constant to x of f of t dt equals f of x. This is only when you have a derivative of an integral. It's kind of weird. This is all about finding a derivative of an integral. And how do I know, how do I recognize it? I look for a derivative of an integral with variables in the limits. Look for, it has to be a derivative, not just an integral with variables in the limits, a derivative of an integral with variables in the limits. You are using FTC, part 1. So, the nice thing about these problems is they're super fast and super easy. Like, so easy, you're going to be like, what? So, the first one, find the derivative of g if g equals the integral from 0 to x of the square root of 1 plus t squared dt. So, what does g prime, because that's the derivative of g, what does g prime equal? G prime equals f of x. What does that mean? All you're doing is taking your f and changing the variable to an x. Done. It almost feels so easy, it feels wrong, right? Okay. Yeah, how do we make this harder? That's a good question, right? Because obviously we're not going to give you 14 problems of change the variable from t to x, right? Okay, so that's where the more general case of FTC Part 1 comes in. Are you ready? Do you have this down? Okay, are you ready now? You got to be ready eventually. Okay, good. Okay, so this is the general form of FTC Part 1. So the general form, that opening form, that was how it was started, right? And then eventually mathematicians ended up expanding it into this. Now, this can actually be derived easier than you'd think. It's actually a simple case of product and quotient, or product and chain rule put together. I used to derive it for my students. I haven't done it in years. I'd have to remind myself how to start the process to get this derived. But once you start it, it's not that bad. It's actually kind of fun. So anyway, but it's just so it's easy to derive. And it looks scarier than it is. These are actually kind of simple and fun. So what does this really say? When you have a derivative, now it doesn't have to be constant to x. It could be some function of x to another function of x. We could go from negative x plus 3 to the square root of x cubed minus 8, right? So any function of x in the limits, right, of some function of t here. All right. So when we have a derivative of an integral with variables in the limits, what do? Plug the top limit into your function times the derivative of the top limit minus plug the bottom limit into your function times the derivative of the bottom limit. I'm going to walk you through the problem we just did using this so you can see that the one that you just did is kind of falls under this umbrella. So we just did the derivative of the integral, I got to look, from 0 to x of square root of 1 plus t squared dt. 0 to x square root of 1 plus t squared dt. So if we were to do this using the more generalized version of FTC Part 1, the first thing you do is take this and plug it in for your t. So you replace your t with whatever's up here. So I get the square root of 1 plus x squared times the derivative of this upper limit. What's the derivative of x? 1. Minus, now you take your lower limit and plug it in for t. So you get the square root of 1 plus 0 squared times the derivative of 0. What's the derivative of 0? 0. Which means if any of this is a constant, it's always going to be 0. The term's going to disappear because the derivative of a constant is always 0. So you end up with square root of 1 plus x squared. All right. Are you ready to try some of these on your whiteboards? Ready? Oh, wait, I lied. Wait. Yeah, the next one's the whiteboard challenge. One practice first. So one on paper, do this one, see what you do, see how you do, and then we'll go to whiteboards. Remember, plug in the top limit times its derivative minus plug in the bottom limit times its derivative. Should be done. Like these should go real quick. I know it's the first time, so you're kind of learning, but these should go real quick. Like you should really enjoy your homework tonight. Okay, so remember this only applies if you're doing the derivative of the integral. Only applies if you're doing the derivative of the integral. Derivative, right? Okay. All right. So what do? We plug in the top limit times what's the derivative of the top? Minus plug in the bottom limit. What's the derivative of the bottom? 1. And then if you want to clean it up, you get 4x cubed plus 6x minus 2x, so plus 4x minus 3. Now, you guys haven't learned how to evaluate an integral yet. When we used to do the parts backwards, you would learn how to evaluate an integral, and then you'd learn this, the derivative of an integral. And the nice thing about doing it backwards is that then we can make you do this by hand first, where you would do this whole integral, anti-differentiate the function, plug in your limits, and you'd end up with some function terms of x. And then when you take the derivative of that, you end up with this. And then we say, look how much easier it is with, FTC, right? And then it's like, wow. So, but we can't do that now. So anyway, yeah, I know. You'll learn it Monday. Shortcuts on Monday. Okay? All right. Okay, on your whiteboards, all 4, begin. All right, so for the first one, plug in the x. Times the derivative of x, which is 1, minus all constants. When you're doing FTC Part 1, all constants are going to go to what? 0, right? So what does this thing equal? It's just the square root of x squared plus 4. Which, if you did that first FTC that I taught you, the simple formula, this is what you just replacing the t with a 4, right? Because when it's constant to x, all you're doing is changing your variable. All right. But now, it's constant to x squared. So when we plug in the x squared into t squared plus 4, Ari, what do we get? X to the fourth plus 4 times the derivative of x squared, which is 2x. Good. All constants still go to 0, so there you go. Hey, if all constants go to 0, does it matter what the constant is? No, because when you're doing this part of the integral, you're generating some area that ends up being a constant, doesn't have variables in it. And so when you do the derivative of that, it goes to 0. So it doesn't matter what that amount of that area is. If it's a constant, it's going to 0 as soon as you differentiate it. So the constant doesn't matter. So you end up with the exact same answer as the previous one. All right. And then this last one, so the constant goes to 0, but it's first. There's actually two ways you could think about this. You could reverse your limits and put a negative in front, right? Or you could just think of this as 0 minus and then do this guy. So square root of x to the fourth plus 4 times 2x. So this one ends up being negative 2x root x to the fourth plus 4. I'm going to take a quick walk around the room. So good. Yes. Yep. Yep. Yes. Oh, wait. Last. Whoa. Those ones in orange have problems. What's wrong with the ones in orange? You have t's. No t's. Those have to be x's. And that's a big deal because what you've written right there is a multivariable function, and you are not in multivariable calculus, right? Okay. All right. Good. All right. Okay. All right. It is time to apply this to an AP problem. Now, I'm going to give you 10 minutes, maybe 12. Again, I'm going to want this on your whiteboards, but I'm going to give you a few hints before you start. I'm telling you right now, and I will tell Ms. Grunwald that I'm telling you this, a problem very similar to this will be on your test. So, get used to it. We will do more of these. This won't be it's not like one and done. We will do more. These are very common. It does kind of. It looks like mountain ranges. Okay. Okay. So let's read through this together. Whoa, stop. Go away. How do I make this? There it goes. Okay. All right. So this, just in case you want to take notes, this is 2016 number 3. So 2016 number 3. By the way, most these problems are appearing more and more frequently on the AP exam, and often, like this is from the AB, but these are often crossover problems where it would also be on BC. So they really like these questions. Now, we're going to walk through. I'm going to give you a little hint, and then I'm going to set you loose, and then I'm going to cut off your time because you probably won't finish, and that's okay, because I want to have time to walk through it. So the figure above shows the graph of a piecewise linear function f. From -4 to 12, the function g is defined as g of x equals the integral from 2 to x of f of t dt. Okay. Does g have a relative max, min, or neither at 10? So in order to find the relative extrema of g, what do you normally need to find first? G prime, right? To find the critical numbers. You need G prime. G prime, well, my goodness. G prime, but That's the derivative of an integral with variables in the limits. Why, it's a major coincidence that I'm asking you this question today, right?
Crazy.
Okay, so it's so good. We just learned the FTC. So what would G prime equal? F of x. So G prime of x equals f of x. Just so you know, for the College Board, whenever you're doing these kinds of problems, you have to write this relationship to get any credit for anything. So once you write it, you're good, you're covered, right? But you gotta write this relationship, and then you're welcome to use these interchangeably. You can write your answers with G primes or with F's or whatever you want to do, right? But let's just take a look. This is the graph of F, which means this is also the graph of G prime. Why, we're back to chapter 4. Okay? All right. So what we have here is the graph of a derivative. And you're going to apply your amazing knowledge that you remember from chapter 4 in order to answer these questions. Are you ready? Yes, ma'am. All right, you have 10 minutes starting now.
Okay.
Pause. I'm sorry. Okay.
Those are good times.
So I'm going to erase this and we're going to walk through parts A and B. I was really hoping you would all get perfect. So let's take a look at part A. So this is the graph of G prime at 10. First of all, the because statement for a relative max or min is because G prime changes from positive to negative or negative to positive. But G prime is always below the x-axis from on the left and right of 10, which means G prime doesn't change sign, which means there is no max or min at 10 because G prime does not change sign at x equals 10. So very nice. Good. You can use F or G prime as long as you link them, which they did, so very nice. Good. Okay, beautiful. Very nice. All right, writing a quick link. Good. All right. Good. Make sure when you're writing your because statement, I know it's feels like extra work, but you should say at x equals 10. Because G prime absolutely does change sign from negative to positive and positive to negative on several places on this graph, right? So you've got to have that at x equals 10, otherwise you're lying. Okay, so that's a graph of derivative.
That's just extra.
Don't put graph is derivative. What does that even mean?
No, it's just supposed to be like a monkey day. It's like stuff for us.
Graph is derivative. Okay, so yeah, don't write that. Okay. That would be something, if you want to write that down, you would put on your scratch work and not in the actual booklet, right? Okay. Neither, because F does not cross the x-axis at f of 10 and therefore does not change sign. Just say, use your because statement, because F does not change sign, done, right? But that's true. You got it. So you got it. I cringe a little bit, but I think you got it. All right. Neither G prime does not change sign. Neither G prime does not change sign. Beautiful. All right. So all of you guys got that one. All right. Point of inflection. If you want to justify this with G double prime, which you absolutely are within your rights to do, you have to then link G double prime to F. So if G prime equals F, then G double prime equals F prime. So now you can use like G prime changing, increasing to decreasing, or you could say G double prime changes sign, or you could say F prime changes sign, or you could say F changes increasing, right? You could use it however you want to, as long as it's correct and you've like established the relationship. So does G have a point of inflection at x equals 4? Yes, it does, because G prime changes from increasing to decreasing, or G double prime changes sign. Just make sure you write the little link, right? Good. Yes. Good. Yes. Because G prime has a relative max there. Okay, and just put G prime changes from increasing to decreasing. Don't add your like extra stuff to your cousins, but it's true. You wrote everything you wrote is true, so that's fine. Good, that's fine. Yes. Yeah, great. Oops, yours is wrong. Because first of all, you used a bad word. Like that's like the worst thing I've ever seen. What is the bad word you have on your board? It. You just said it. Yeah. Cusp is fine. A cusp is another word for a sharp turn. So that's like heavy math. So did you know the word cusp? That's how Grumel said it? Yeah. Cusp is absolutely correct. Okay, so let's talk about this. Two things. First of all, is G prime defined at 4?
Yes.
Yes. There is a point right there. It's 4. G prime of 4 is 4. This is the graph of G prime, right? Now, is G double prime defined at 4?
No.
No. Is that okay?
Yes.
Yeah, because points of inflection and relative extrema occur when those derivatives are either 0 or undefined. Just because the derivative is undefined doesn't mean the function's undefined, right? The function is the original G defined at 4? Yeah. It has to be, because if it wasn't, G prime would not be defined there, right? So G has to be defined there, which means since G prime is changing from increasing to decreasing and G prime exists, G has to exist, and therefore there's a point of inflection. Yeah. All right. That's good. That's good enough. All right, let's move on. Absolute max and min. This is where most of you are kind of just getting your feet wet. So, absolute extrema on a closed interval, when we have to find out, oh, I see one board that was just starting. When we find absolute extrema on a closed, oh, I see a couple. Ooh, I'm doing some oohs. Okay, all right. Ooh. Okay. All right, as my kids, there's a chef that works on thing. There is a character that always go, ooh. So anyway, okay, that's what my kids would say if they heard me go, ooh. Okay, so absolute max and min, you find your critical numbers and you test your critical numbers and your endpoints by plugging them into the original function. We're finding max and min of G, so G, that's our original function. So our critical numbers and our endpoints, critical numbers would be where G prime is 0 or undefined. Is G prime ever undefined? So our critical numbers would be -2, 2, 6, and 10. We have a lot of testing to do. So we have to test G of -4, G of -2, G of 2, G of 6, G of 10. Technically, oh, and 12. Sorry, I didn't even see the endpoint of 12. You could technically skip the 2 and the 10 because we know that those are not maxes or mins. Because the first derivative doesn't change sign. So you could skip those, but you got to test everything else. I'm going to start with easy ones first. So even though we don't have to test the 2 is the easiest one. So let's go ahead and test it, right? So if we plug in a 2, we get the integral from 2 to 2 of f of t dt. What's the integral from 2 to 2?
0.
0. We all got that one, right? Plug in a 6 into your g function. This is the integral from 2 to 6. The integral from 2 to 6, that's the area under our f curve from 2 to 6. 1/2 times 4 times 4. This guy has an area of 8. So that guy's 8. G of 10. By the way, the College Board wants you to write all these integrals. 2 to 10. Did I do something wrong?
You got low battery.
Oh,
Your
I
Mac
think we
needs
can
to
make
change.
it. We'll see.
5%.
Yeah, we can do this. We got this. All right. 2 to 10. This is 8. This is 8, but it's negative. So the integral from 2 to 10 is going to be 0. The integral from 2 to 12, well, that's going to be 0 plus whatever this integral is from 10 to 12, right? This is 8, this is 4, except it's negative. All right, now we're going to use the property. If I do this integral from 2 to negative 2, oh no, we're high to low.
No.
You got to flip it and make it negative. This is negative the integral from negative 2 to 2, which essentially should teach you that whenever you're doing an integral backwards, the signs all get reversed. So what's above becomes negative and what's below becomes positive. But all you have to do is just reverse, make it negative, and then just do it normal and you'll be fine. So from negative 2 to 2, again, this is 8, but there's a negative in front. So this integral is negative 8. Last one. So we have 2 to negative 4. All right, this is negative the integral from negative 4 to 2. All right, so from negative 4 to 2. So this guy, that's a 4, but it's normally negative. So we'd have a negative 4 plus 8. So we'd have a net area of 4, but we got to multiply it by negative 1. So we get a negative 4. All right, so our answer, so negative 4, negative 8, 0, 8, 0, and negative 4. What's the max?
8.
8. What's the min?
Negative 8.
Negative 8. Done. Any because statements? No. All right, last problem. I know this is kind of messy, but the last problem is kind of fun. Find all the intervals where g is negative. Remember, g isn't just the area above or below. G is the integral from 2 to x. So from 2 to 6, we know g is positive. What about from 2 to 10?
Still positive.
Still positive. Because you've got 8, and then you're subtracting, right? But you're still positive, right? So if we start at 2 and we go all the way to 10, we are positive, we're subtracting, but we're still positive, and we hit 0 here. So g is negative, or g is negative from 10 to 12, because that's when we're truly going negative. And in reverse, we go backwards from 2 to negative 2, we are negative because we're going backwards. And then even though we're not adding enough, we're still negative. So g is negative from negative 4 to 2 and from 10 to 12.
But it's less than 10.
Yeah, that's okay.
So wouldn't it be 0 at 10?
So that's what I said. So your answer to this would be negative 4 to 2, including the endpoints, and 10 to 12. Is that okay?
I'll figure it out.
Okay, question, yes.
Why did you start at 2?
Because that's how they defined G,
Oh.
right? Okay, Anisha.
What were the because because like it's
There is no because. They didn't even ask you to justify. They just said, what's the answer? Yeah. Good. Other questions? Okay, we made it.